Anyway, now what I want to do at the top here is I want to show that esters and acids are functional isomers. Those of you that were here on Saturday, what is isomers again? It's like a twin. An isomer is like a twin. Okay, now what do we mean with twin in brackets? We mean that they have the same molecular formula. Okay, and this here that I gave to you is a molecular formula, or a molecular formula. Okay, now I want to start with the carboxylic acid. When the carboxylic acid has 3 carbons, all right, what will the name of that acid be? Propanoic acid. Propanoic acid. Okay. And what does the functional group of an acid look like? What's going on? Who does not have notes?
What does a functional group of
A carboxylic acid look like?
it's C, a bond, then O, then H, and then a double bond, oxygen.
Well done. All right, so that is the carboxylic acid's functional group and a carboxyl group. But our carboxylic acid, propanoic acid, must have 3 carbons. So 1, 2, 3. 3 carbons, and we can fill in our hydrogens. Antoinette, why does this carbon not have another hydrogen there? Four? 4 hydrogens, 4 bonds. It already has 1, 2, 3, 4 bonds, so there's no space for another one. All right, so that is propanoic acid. Now, what we say with an isomer is we can take that same parts, that same number of carbons, oxygens, hydrogens, and so forth, and we can make an ester with that. Okay, now we can make actually 2 esters with that. So I want you to say there and there. Oh, no. Where and where now? Alright, so I want you, there you go. So I want you, on the right hand side there's a block. I want you to make 2 arrows, an arrow to the top and an arrow to the bottom. Right, you're gonna, in that block, you're going to make 2 drawings. Okay. Now, what does the functional group of an ester look like, Princess? Yo, Princess. A double bond. Okay. Right, now, see, I went too fast. Okay, so we have carbon, double bond, oxygen, oxygen. Okay, and so I said you must make 2 arrows, an arrow there, arrow there. Okay, I want you to do another one. Carbon, double bond, oxygen, oxygen. Alright, so what are we busy with? We're busy with making an ester with all the parts that we have when we made the carboxylic acid. The carboxylic acid's molecular formula was C3H6O2. If you look there at the top. So we must now make an ester with the same parts. We already used our 2 oxygens in both. Right? Now we have 3 carbons. Here we already have 1 carbon. to make an ester, you must have at least have another carbon there. Where are we going to put our third carbon? Anyway, let's say we put our third carbon there. And we fill in our hydrogens. Then that will be considered an ester. But instead of putting our third carbon there, we could have also put our third carbon here. This will also be an ester. And both will have 6 hydrogens. Guys, I'm just going to draw it here. Alright, now my first question is, I'm going to have 2 questions. My first question will be, what is the name or names of these esters? And Jabu. What do you say? What will the name be? We did a few examples of it there at the bottom. I think this is a lollipop type of question. Okay, yes, Tawana? Are you taking a guess for which one? Okay, the top one? No. Yes. What? No, it's not. Okay, let's just check. I'm going to go to the ones that we did here at the bottom. Let's go to propyl methanoate. Okay, yes, Boki? Go for it, go for it. Well done. Ethyl methanoate. Good job. Alright, so YF, I can see there is my main structure, my functional group. So anything that is not in my main structure here is my side chain. Okay, so my side chain here has how many carbons? 2. What do I call 2 carbons? Ethyl for side chain. And then on my main chain, how many carbons do I have? 1. 1 carbon is called meth. Oopsie. Meth. And the suffix for an ester is methanoate. Say again, Boki. What do you want to ask? Are you sure? All right. My question is, what is the name of this one? No, you are done answering. Chup, 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 chup. It's just me and Boki eating lollipops. Yes, Oana?
I'm not sure.
Okay.
Methyl. Is it well? I'm confused because of the 2
I'm gonna start. Wait, I'm gonna start. There.
main chain. It's methyl, methanoate.
Methanoate? How many carbons are on my main chain?
1.
Uh-uh.
Oh, 2.
So it is?
Methanoate.
Alright. So this one will be... Oh, I don't have any space left. This one will be called... methyl ethanoate. Okay. So we just practiced a bit of names, but what I want to show you is that with the same number of carbons, hydrogens, and oxygens, we made a carboxylic acid and we made esters. So with the same pieces, we made two different functional groups. We made two different homologous series. Okay, so that is why they are called functional isomers. Because they have the isomers, twins, same number of everything, but the functional group changes. This is an ester, this is the carboxylic acid. This one smells nice, this one tastes sour. Alright. Okay. But we're going to do that again and again. So that was the esters. Now I want to go to the concept of isomers. Okay. You have 4 definitions to study here. The first one is just isomers. So the general definition for isomers is organic molecules with the same molecular formula but different structural formula, so differently put together. So made up of the same particles, but they're just differently put together. Okay, now we're going to have 3 different types of isomers. We're going to have chain isomers, positional isomers, and functional isomers. Okay, let's first look at the chain isomers. The definition there is this again, the same molecular formula, but different types of chains. And I want you to put in brackets there for yourself, different. Delta means different, or the changing. Different length of parent or main chain. Okay, so with a chain isomer, the length of the parent chain is changed. Okay, so the example that I give you there is butane. But means what again? 4. So here we can draw in 4 carbons. 1, 2, 3, 4. And ane tells us it's part of the alkane homologous series. What is the general formula for the alkane series? CN. Yes. So what will butane's molecular formula be? 4H plus 10 plus 2 is 10. Yes. So when we draw the isomer for butane, it must also be that. We will get to that in a moment. Okay. It must. The isomer of butane must have the same molecular formula. That is a must. It can't have an oxygen or one less hydrogen. It must be exactly the same number of molecules. Alright, but now the isomer, the chain isomer, it must have a different length of the parent or the main chain. Can we make it 5 carbons? No, because we only have 4 carbons. So what are we going to make it? Mosi? Okay, so Mosi says, now don't draw. Mosi says we must go like this. Yes, that's what you say. Don't draw it just yet. What will that thing's name be? Butane. But we cannot have butane again. It must be another molecule with another name. Different number, different chain length. It must just be the same number of things put together. Yes. Wait. This is your chapter, this one, Purwana. Alright, let's just check. 4 carbons, 4 carbons. Let's check the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they are called isomers. Because exactly the same number of carbons and hydrogens, but it's a different chain. What is that thing's name? Yes, for propane, but what is the suffix, or what is the, we have a side chain on there? So it will be called, you can either say 2-methyl, but it can only be on the second one. So it will be methyl propane. Right, let's look at the next one. And positional isomer. Okay, so there it says the same molecular formula. So again, same molecular formula, but different positions of either the side chain or the substituent, like a chloro, bromo, iodo, fluoro, or functional group on the parent chain. So the position of the what changed. Okay, so if we look here at 1-chloropropane, pro means 3 carbons, 1, 2, 3. And on the first chlorine, on the first carbon, there must be a chloro. So what will the general formula be here? C3 not the general, the molecular formula, sorry. The general formula is CnH2n plus 1x. Ne? Okay, so now we must take these exactly the same number of everything. Now this is not an chain isomer. Okay, so the parent chain stays the same. Not a chain isomer, the parent chain stays exactly the same. 1, 2, 3. Only the position, the positional isomer, the position of the weird thing must change. So the position of the weird thing must change. Can it be on the third carbon? What will this one's name be if it's there? Will it be called 3-chloropropane? No, because you're going to start counting from this side then. It will still be called 1-chloropropane. So it cannot be on the third one. The only position that it can be is the second one. Then it's called 2-chloro. Could I have put my chlorine here on this side, like this? So it was here, now it's there. No, it will still be 1-chloro. If I put it here, it still be called 1-chloro. Okay. Right, and then the last type of isomer that we have is an functional isomer that we just did. What is a functional isomer? Same molecular formula, but different functional groups. Different functional groups. Okay, right. Now we only get 2 functional isomers. 2 types. Okay, so we're going to do this one and this one. First, we're going to look at methyl methanoate. To which homologous series does methyl methanoate belong to? Esters. Okay. And esters can only be functional isomers with carboxylic acids. They cannot be a functional isomer with anything else. They can only be a functional isomer with a carboxylic acid. Okay, so I'm going to, for myself, going to start with the functional group for an ester. What does that look like again? C-double-O-O. Right, and after that oxygen, there must be a C. Okay, so let's just check. Did I draw this correctly? Methyl, methyl, methanoate, methanoate. So now I can just put in my hydrogens. So what is this one's molecular formula? Will be C2H. How many hydrogens? 4. How many oxygens? 2. So Declan, from there, can we make a general formula? CN to go from 4 from 2 you had to say times 2, so it's 2N. And how many oxygens? 2. Okay, so now we must draw an carboxylic acid with exactly the same number of carbons, hydrogens, oxygens. So carboxylic acid with exactly the same molecular formula because they are isomers, or they must be isomers. A carboxylic acid's functional group, what does that look like again? C. That must be there for it to be a carboxylic acid. Okay? How many carbons must we have? We must have 2 carbons. 2 carbons. So 2 carbons. Let's check. 2 carbons. Chop. Well, how many hydrogens? 4. 1, 2, 3. And there's the 4th one. How many oxygens? 2. What will the name of this carboxylic acid be? How many carbons? 2. What do we call 2? Ethan. And what's the suffix for an ester? Not an ester, carboxylic acid? Oic acid. Ethanoic acid. Alright, so they are called functional isomers. Isomers because they have the same molecular formula, but they are from different functional groups. This one is an ester, this one is a carboxylic acid. Let's look at the next one. A propanol. To which homology series does propanol belong to? Anal. Aldehyde. An aldehyde. And aldehydes can only be functional isomers with ketones. Okay, propan, how many carbons? 3. 1, 2, 3. What does the functional group for an aldehyde look like? There's a double bond on the first or the last carbon. Okay, and then we have our hydrogens. So the general formula here will be C, the general and the molecular formula, C3H, how many H's? 6, how many oxygens? 1. So we must draw an ketone with exactly the same number of carbons, hydrogens and oxygens. So we start with our 1, 2, 3 carbons. Now, the functional group for an ester, what does that look like? A ketone. Double bond, oxygen where? In the middle, not at the end. In the middle. What will this one's name be? Propan, ne? Because pro for 3, and for single bonds between carbons. And then, what's the suffix for a ketone? One. Ketone is an one. So this one will be called propan 2-one. Propanone. Can it be propan 1-one? No. Can it be propan 3-one? No. So it's actually redundant to put that 2 in. It can only be propanone because it can only be on the second one. Can't these two be positional isomers? Because the carbons are 3-3-3, so the parent chain is the same. It's just the position of this weird thing that changed. Can these be called positional isomers? Cannot be. Because when the position of this changed, the functional group changed. Okay, this is called a carbonyl group. This is called a not a formal group. This is called a carbonyl group. Okay, so they cannot be positional isomers. They are functional isomers. All right, sharp. Now I realize I cannot take in your notes because I want to give you homework. Damn it. Okay, so the homework I want to give you is on page 28.